Hi guys, welcome to our third video in chapter 17. This video is going to cover section 17.3, which is all about rate laws. Okay. So this video gets pretty fun because rate laws are a mathematical equation that describes the relationship between the rate of a chemical reaction and the concentration of the reactants. Or another way to think about this is I am trying to calculate the concentration of my product or reactant, my species, over time. Okay. And so that rate, the rate law, is given as K times the concentration of our substance, where K, it's lowercase cursive a, is called the specific rate constant. Okay. This number it's defined right below. It says it is a numerical value that relates the reaction rate and concentration of reactants at a given temperature. Some very important things to know about K, our specific rate constant. It is found experimentally, which means that you will need to look it up in a table. It will be given or you will be calculating it. It's not something you can memorize, okay? K is independent of concentration. It is independent of temperature. It is constant for our purposes. So we should consider K and our reaction rate constant, in fact, to be a constant. Doesn't change. We're going to talk in a moment about reaction order. K actually has different units based on the reaction order. So sometimes it will be in liters per mole per second. Sometimes it'll be in liters squared per mole per second. And other times it'll be just per second or second minus one. And so I'll explain a little bit about reaction order, and that will potentially make sense. Potentially it will be something you just got to remember sometimes the different units for K. It should also be given based on the information in the question, okay? Or you should be able to derive these units from the question itself. So let's talk about this strange concept called reaction order. And this is definitely a new concept, but it is something that we find experimentally, and it's actually very important. So the reaction order defines how the rate is affected by the concentration of a reactant, right? So this is actually a qualitative value, the reaction order, which means that we're looking at it and we're going to say doubling this concentration does what to our rate or something like that. So this is, again, another thing that is found experimentally, right? Another thing that's found experimentally. So that's good for us. No memorization, just working with this stuff. Okay. Um, and let's look at this example. I like to go into the decomposition of hydrogen peroxide, H2O2, to form hydrogen and oxygen gas. I've written out the equation here where we have H2O2L going to H2 gas plus O2 gas. And I said our rate is equal to K, our specific rate constant, right, times the concentration of our hydrogen peroxide raised to the first power. This actually tells us that this is a first order reaction. So we go back at our units and we say, cool, it's first order reaction. That means the units are mole per liter times second. Okay, so that's our units there. Okay. So the way that we get this is actually experimentally. And what we do, and I actually think this is a pretty decent picture over here to look at and examine this. And what we will do, I'll zoom in a little. What we do is we go ahead and we do the reaction and we vary the concentration of a reactant. Let's say we are looking at the concentration of A going to B, and we change that concentration. We have none, and then we go all the way up to maybe 100 molar, something like that. And we see how does our rate of reaction change with that varying concentration of our species. And so for this all the way to the left, this is a weird one, actually. So we'll start here with our zero order raised to the power of zero. Well, in this example, as I increase the concentration of A, I actually see that my rate flatlines. So the rate does not change based on the concentration of A. So it's completely independent, right? It makes a linear line. When I graph my concentration of A over time, I see that it just steadily decreases. Regardless of the concentration of A, that reactant is getting used up at the exact same rate. It is a linear line. And because of that, our rate is actually said to be independent of the concentration of A. And so if we raise that concentration of A to the power of 0, anything to the power of 0 makes it 1. And so our rate would just be equal to our specific rate constant in that. So that's called a zeroth order reaction, one where the concentration of our reactant actually doesn't affect our rate. This is not the most common, but it can be somewhat common. It can be something you see. Example would be if we are looking at plating copper onto a zinc electrode, while the concentration of our copper is going to not really affect our rate of reaction because it will constantly be replenished. Okay, so this is an example of a zero order reaction. A more standard type of reaction is called a first order reaction, where when we vary our concentration of A, we do see a change in our rate. And so, for example, in this first order reaction, if we double the concentration, we also double our rate law. If we triple our concentration, we also triple our reaction rate. Okay, so what we do to our concentration also happens to our reaction rate. Well, that is a one-to-one change, right? What I do to my reaction, I will also do to my rate. And so that is said to be a first order reaction. So the concentration of my reactant just directly affects my rate of reaction. And so I raise the power of my concentration of my reactant to the power of 1, because that's a first order reaction. Now, next, if I think about my second order reaction, second order is kind of cool. Maybe I double my rate of or my concentration of A, and that results in a quadrupling of my rate of reaction, right? Or if I triple my concentration of A, then that really results in a 9 times increase in my rate of reaction. Well, that isn't a linear relationship. That is a exponential relationship. And so we say that would be a second order reaction, or we would raise our concentration of A to the power of 2 for that rate law. Okay. So again, our reaction order, these are things that we find experimentally, right? Just some notes real quick before we go on. I do have some examples that I can talk about here, but just some notes, right? Our first order is going to make a straight line when we graph concentration versus time. Our second order reaction is going to make an exponential line when we make a graph of concentration versus time. And then our zeroth order will just make a flat line, okay? A flat line. So that's just some notes about how this reaction occurs. And then in general, right, I think this is important to remember. In general, the overall reaction order is the sum of all of the elementary reactions occurring. That is essentially Hess's law, right? We can add up these reactants. So if I want to make this general, and I want to turn this into something that I can apply to any kind of equation. Let's look at the hypothetical. A plus B goes to C, where lowercase letters are my coefficients. That, maybe I have 2A plus 3B goes to 1C. That would be my lowercase letters. And then my capital letters are the actual species. Well, my rate law is actually going to be our specific rate constant, K, times the concentration of A raised to the power of A's reaction order, and times the concentration of B raised to the reaction order for B, okay? So for a first order reaction, the coefficient in my rate law will be the coefficient in my reaction. So in this case, lowercase a would be M, and lowercase b would be N, if that's what I see in lab, right? And so an actual example, which we can't do because we don't have a nitrogen monoxide tank, but one that can be done in lab fairly easily, is for somebody to combine nitrogen monoxide with hydrogen gas and form nitrogen gas plus some water. And they've done this experimentally, and what they found is that our rate is equal to some constant times the concentration of our nitrogen monoxide raised to the power of 2 times our concentration of hydrogen gas also raised to the power of 2. Right. So this tells us that this is a first order reaction because we have our coefficients being found in our rate law. Okay. All right. So moving on here, we Sorry, guys. I want to make sure I wasn't being redundant. But yeah, anyway, as I was saying, we do need to determine these reaction orders experimentally, and it's actually not that bad. I know this video is a lot of math, a lot of words, a lot of stuff, but it's actually not that bad. So let's look at how we would do this using what's called the method of initial rates. Okay. The method of initial rates is used to determine the reaction order for a specific reactant by examining the initial rates of reaction carried out with varied reaction concentrations. So here is some data that might have been collected, right? We're combining A with B to form some products. Well, if I look at trial, what's going on here? If I look at, yeah, there we go. If I look at my trials, I don't know why there's like an A with a line or A with an accent, but I'll replace that with reaction arrows. So let's say that I'm looking at trial 1 to trial 2. Well, some important things to note is that my concentration of B was not changed. So in this case, I am holding the concentration of B to be constant, and I am doubling my concentration of A. So from trial 1 to 2, I double the concentration of A. Well, what happened to my rate? I went from 2 times 10 to the negative 3 to 4 times 10 to the negative 3. That is a doubling of the reaction rate. So if I double my concentration and that doubles the reaction rate, we are in a first order reaction. So we say A so the reaction is first order in respect to A. Okay, so with respect to A. Now next, I'm going to erase some of this highlighting because next I want to look at the next movement I had. So let's look at what happened when I went from trial 2 to trial 3. Well, I start at 2.2 and I end at 0.2 concentration of A. So this time A is actually being held constant. And then my concentration of A is constant. And I double my concentration of B. I go from 0.1 to 0.2. Well, the rate goes from 4 to 16 times 10 to the negative 3. So I quadrupled the rate. If I double my concentration and I quadruple the rate, that is said to be a second order reaction. Okay. And so if I were going to write the overall rate for this reaction, the rate law, I would write my rate is equal to my specific rate constant times concentration of A to the power of 1 because it's first order times concentration of B to the power of 2 because it is second order. All right, guys, that's all I have for this video. Thank you for listening, and I'll see you guys in the next one.